Welcome to the intricate and fascinating world of polymers and giant covalent structures. These materials, formed through covalent bonding, are fundamental to both natural processes and human-made innovations. Polymers are large molecules made up of repeating units called monomers. These monomers are covalently bonded together in long chains, creating materials with a wide range of properties. Monomers. Polymers start with small molecules known as monomers. These monomers contain double bonds or functional groups that can react with each other to form long chains. Polymerization. The process of forming polymers from monomers is called polymerization. There are two main types, addition polymerization and condensation polymerization. Addition polymerization involves monomers with double bonds. For example, ethene C2H4 molecules react to form polyethene or polyethylene. Condensation polymerization involves monomers with functional groups that react to form a polymer in a small molecule, often water. For example, nylon is formed from a diamine and a dicarboxylic acid. Polyethylene, PE, monomer, ethene, C2H4, use, plastic bags, bottles, and containers. Properties, flexible, durable, and resistant to moisture. Polyvinyl chloride, PVC, monomer, vinyl chloride, C2HCl, use, pipes, capable insulation, and clothing. Properties, strong, lightweight, and resistant to chemicals. Polystyrene, monomer, styrene, CCNH, use, packaging materials, disposable cups, and insulation. Properties, lightweight, good insulator, and easily molded. Nylon, monomers, hexamethylene diamine and adipic acid. Use, textiles, carpets, and fishing lines. Properties, strong, elastic, and abrasion resistant. Versatility. Polymers can be engineered to have a wide range of properties, from flexible and soft to strong and rigid. Lightweight. Many polymers are less dense than metals or ceramics, making them ideal for applications where weight is a concern. Durability. Polymers are often resistant to chemicals, moisture, and wear, making them long-lasting materials. Thermoplastic and thermosetting. Thermoplastics can be melted and reshaped multiple times, e.g. polyethylene, polystyrene. Thermosetting plastics harden permanently after being shaped once and cannot be remelted, e.g. epoxy resin. Giant covalent structures, also known as network covalent structures, consist of a vast number of atoms all interconnected by covalent bonds, forming a giant lattice. These structures result in materials with unique and impressive properties. Diamond. Structure. Each carbon atom is tetrahedrally bonded to 4 other carbon atoms, forming a 3-dimensional network. Properties: extremely hard, high melting point, excellent thermal conductor, and transparent. Use: cutting tools, jewelry, and heat sinks. Graphite. Structure. Each carbon atom is bonded to 3 other carbon atoms in a hexagonal layer. These layers are held together by weak van der Waals forces, allowing them to slide over each other. Properties: good electrical conductor, slippery texture, high melting point. Use: pencil leads, lubricants, and electrodes. Silicon dioxide. Quartz. Structure. Each silicon atom is bonded to 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms, forming a 3-dimensional network. Properties: hard, high melting point, transparent, and insulator. Use: glass, ceramics, and electronic components. Silicon carbide. Structure. Each silicon atom is bonded to 4 carbon atoms, forming a very hard, strong lattice. Properties: extremely hard, high thermal conductivity, and chemically inert. Use: abrasives, cutting tools, and high-temperature semiconductors. Properties of giant covalent structures are high melting and boiling points. The strong covalent bonds throughout the structure require a lot of energy to break, resulting in very high melting and boiling points. Hardness. Materials like diamond are incredibly hard due to the extensive network of strong covalent bonds. Electrical conductivity. Graphite is an exception among giant covalent structures, as it can conduct electricity due to the delocalized electrons within its layers. Most others, like diamond and silicon dioxide, are insulators. Chemical resistance. Giant covalent structures are usually chemically inert, making them resistant to polymers. And giant covalent structures represent 2 remarkable ways atoms can bond covalently to create materials with diverse and valuable properties. Polymers, with their versatility and range of applications, are essential in modern life, from plastic products to advanced textiles. Giant covalent structures, with their exceptional hardness and stability, are fundamental in both natural and industrial contexts. from the hardest minerals to everyday materials like glass. By understanding these substances, we gain insight into the incredible complexity and utility of covalent bonding, opening the door to innovations and applications that enhance our lives and our understanding of the material world.